I'm glad to introduce the next session and the first speaker. So now we talk about satellite quantum communication. And the speaker is Julian from Tesla Spacecom. He has a career at MIT, at the University of Hamburg, and École Normale Supérieure. And the floor is yours. Thank you.
Yes, first of all, thank you for the introduction and to Christian for inviting me. I'm not sure if this really works. Yeah, it works. Okay, great. Yes, so actually, a few words about me. My academic background is actually not quantum communication. It's quantum many-body physics, ultra-cold atomic gases. So I did kind of a switch back in 2021 when I moved from academia into industry and went to a space company. So bear with me. I'm also not an expert in quantum communication. So I will try to talk a bit about kind of like an industry perspective of transitioning technology from research labs into a commercial application. I'm not saying that we're there yet, but we're on the way. And actually, we have a lot of projects where we're directly collaborating with academia and research institutes and so on. And in the end, I will also say a few words about upcoming collaboration with Christian. So back to the spirit of this talk. A few words about the company, about TESAT. So we're located in Bagna. That's not in Thailand, but that's in Germany. I was disappointed myself. So that's actually how it works. That's about 25 kilometers northeast of Stuttgart. Still reachable by public transport. I mean, in terms of not too long, like half an hour. And our core business is satellite payloads. That means we are manufacturing equipment, sub-components that go onto satellites. We're not manufacturing satellite platforms themselves or rockets or anything. We're just manufacturing equipment that goes as the commercial payload onto these satellites. The company itself has kind of like an interesting history. We changed our name quite often. The company itself is a successor of AEG Telecommunications, which was created on that site in 1949. Since the 70s, we're producing space equipment. And as of 2001, we were bought by Airbus Defence and Space. We're now an independent subsidiary of Airbus. Meaning that we can decide on our own what we're developing, and we can, for example, also bid against our parent company, which is sometimes a problem. But, so we have some independence, but we also have a lot of collaboration with ours. We have about 1,100 employees on site. This is our only site with a little star. We have a small site, which is, from a formal point of view, separate from us in the US, which is for let's say, export control reasons and military connections, where the US doesn't want us to see anything that they're doing with our products. But that's a small site. That's like 20 people, I think, in the US. And we have an annual turnover around 300 million euros. And we have a lot of clean room and manufacturing sites in Bagna. And our main fields of activity are basically telecommunications with over 70%. So what we're producing is basically related to the telecommunications, satellite telecommunications, SATCOM. Then the second largest area is Earth observation. And then the smaller parts, navigation. So we are recently contributing to Galileo, to this European Global Positioning System. And we also have a small fraction of science contributions. So, for example, I think a very nice one is we provide the laser for LISA Pathfinder, which is the precursor mission, the test mission for LISA, which is the in-space gravitational sensing mission, which basically reflects the Earth first interferometers just on a much larger scale around the Lagrange point. So this is kind of the fields that we're active in. This is an overview of the kind of equipment that we're producing. As you can see, most of it is radio frequency equipment, transmit, receive. We're also building larger systems. Most of the stuff is then kind of like on-demand customer projects where we really don't have a product, but we do design something according to specs. And then the department that I'm working in is the optical communications department, or laser systems development department, which was created about 25 years ago, where the company also with a lot of investment saw the laser communication field as an upcoming field, and it actually took quite some time. In 2007, I think we had the first laser terminal in space, and only now, since 2 or 3 years, we really see a market developing. So over the last 20 years, we basically sold, I think, 1 terminal per year, really slow turnover, a lot of investment, and now, as of 2021, 2022, we have sold around 1,000 terminals. So there's a lot of constellations coming up now, all in the spirit of SpaceX and Elon Musk. And there's really kind of a huge market change now. Everything has to be much cheaper, doesn't have to be as reliable as before, and has to be produced in much faster rates and so on. And this is kind of nice because actually shows a bit that our company is willing to invest a lot of money with a turnaround that they expect only in 10, 20 years. And this is a bit also the direction that we're going into now with QKD, or quantum communications, because nobody in the company expects that we're going to sell QKD modules in the 800th in the next couple of years. Okay, so as I said, the kind of laser communication development in our company was also a little bit the entry to quantum communications naturally, because all of the quantum communication typically happens optically. So this is our current product line in the optical communication market. We are only producing the equipment for the satellite segment, for the space segment. We're not producing ground stations. We have a test ground station in Tenerife that we also use, but it's not for commercial application. I mean, it's basically for testing our own equipment. It's shared between ESA, us, and DLR. So for the satellite segment, we have these 3 kind of sizes in terms of terminals. The smallest one is the SCOT 20. The numbers behind it, SCOT stand for scalable optical terminal, and the numbers behind are the aperture size in millimeters. So this one is very small. It's 20 millimeter aperture size, and you can understand that the smaller the aperture size, the larger is the diffraction of the laser beam, and the least range you have in terms of diffraction losses. Basically, the less light comes after a certain distance to the receiver. So the smaller the aperture, the less effective range you have for your communication. So these small terminals are supposed to go on so-called CubeSats. So this form factor is 10 by 10 by 10 centimeters. This is 1U, and the CubeSats are basically 3U, 6U. And then we have larger platforms. This one is now the most sold one, the SCOT 80, which has 80 millimeter aperture, and SCOT 135, which has 135 millimeter for the longest range, so up to 80,000 kilometers. And they are all meant for inter-satellite communication and down to Earth. So actually, most of the applications that we're doing is between satellites and not satellites to Earth, which kind of underpins this constellation idea of having like a mesh of satellites around Earth that talk to each other. And it's also market driven. It's all in the optical C-band, so it's all telecommunication band. It's not because it's physically the best solution. It's just where the market sits and where the products are the cheapest and where you can the most easiest connect yourself to ground segments. So that's 1530 nanometer to 1560 nanometers. So it's what you have in the fibers. When you plug in your modem to telecom fibers.
Sorry, this is the sender, right?
This
not
is
the
on
receiver.
Say again.
The large one.
Oops.
Is that sender? I mean, sending the signal only, right? Not receiving signal.
You're talking about what? This one?
Yeah.
These are bidirectional terminals.
Bidirectional.
I mentioned these are basically the optical parts. You have the telescope, you have the pointing mechanism, the coarse pointing mechanism for these two units, which can rotate by 360 and then have some restricted angle in this direction. I think it's 55 degrees for this unit, and I'm not quite sure what the angle is for that one. And you don't have any coarse pointing for this one, meaning that the satellite has to point itself. But this modem here, this is where the laser sits and the communication unit sits, and this one is bidirectional. So the telescopes are designed in such a way that you have send and receive capabilities. So you have typically two wavelengths. I think there's an American standard that we're using right now from the Space Development Agency that we co-developed. I think we have two channels, 1535 and 1553. And you can switch ambidextrously between the two and use them for send and receive.
Okay.
And this can happen simultaneously, which is crucial because for the intersatellite links, of course, your terminals need to be capable of communicating both ways. So again, in these units, in these communication modems, you have send and receive units. And this is, by the way, the coding mechanism for this optical communication is very simple. It's just on-off keying. It's on, switching the light on and off. And actually, in our first products, technologically wise, it was much more advanced. We used phase shift keying, but again, it was too expensive. The market wanted something cheaper, and now we're using on-off keying. Might come back actually if we need higher data rates, because at some point on-off keying doesn't work anymore, and some customers are asking now for 100 gigabits per second, which probably brings us back to phase shift keying. Now, so how did we come to quantum communication in the first place? So about the time when we had the first terminal in space, 2007, which was this guy here, our legacy terminal, which was, by the way, much bigger than the ones I just showed you and much more expensive. I think it was at least one order of magnitude more expensive than all of the terminals that I showed you on the slide before. And there was an interest by ESA and by several academic partners to actually look into space segment for quantum communication and quantum physics experience in general. And we were lucky that at that time we were the only European industry player who had like laser terminals in space. So they came to us, and back in the days it was just a study. This quantum information and quantum physics in space study was then released. Actually, my boss is down here. And there were actually quite a lot more players involved there, Harald Weinfurter, Anton Zeilinger, and it's a bit sad because actually, if we would have followed up on this, and this was really a technical study with like designs for entanglement and for prepared measure and for quantum teleportation, we could have been before misused, but it was politically decided that this is nice but not worth the money. So then there was a huge gap, about almost 10 years, where not much happened. And then in 2015 there was a drive to start QKD again from space, which might have nothing to do with misuse. I'm just joking. I think it was heavily driven by misuse. It was kind of a Sputnik effect for Europe. And there was funding coming up again, and we started to collaborate again with academia. We had a paper with University of Erlangen together, where we actually used the existing terminals, which were back then the phase shift keying, to measure, for example, quantum properties of coherent states, checking whether the quadrature components and the uncertainty, the variance in the quadrature components, are affected by atmospheric turbulences and so on. Turns out they're not. Actually, they're still quantum limited, even from a geostationary orbit to Earth, so about 36,000 kilometers, which is a huge range, which was a nice experience.
What means quantum limited in this sense?
So that the variance of the coherent state it's basically a coherent state. That's what it means. So that the variance is proportional to the mean number that you have in the state, which is a little smaller shown here. So actually, here the expectation value of that quadrature component is, I think, 2, and it goes down. you still see that the variance doesn't really change. So that is basically the excess noise that you have over the quantum limit. But again, these were kind of like I would say quick measurements that one could do based on existing space assets, because typically you don't launch anything within 1 or 2 years, which is dedicated for a quantum mission. So that back in the days, this was really a drive from Misius, showing that Europe can also do something. And right afterwards, there was actually a big drive also from industry towards ESA and the European Commission to start funding a program to bring Europe's own quantum satellite in space. And this kind of like started with ESA, the ESA Quad study, which was a hardware precursor study where DLR, Friedrich Alexander University in Erlangen, and so on, started to develop transmitter architectures and so on, that were then kind of translated in a later phase to something that could be made space ready. And this is a quite beautiful story, because the phase ended, and the study phase ended in 2022. And now, since 2020, same year, we actually have a fully funded space mission that is supposed to be launched in 2026. So that one is called Eagle-1. It's a public-private partnership. There is industry putting money in there, so there is a commitment from industry. We ourselves put 25% of the mission regarding our parts of the mission in there. Then the European Commission and ESA is also putting money in. So we kind of co-finance our equipment, not the whole launch and everything, because that would be extremely expensive. That comes from the European Commission. And there's other project partners involved. There's a big service provider from Luxembourg, which is traditionally into SATCOM involved, which see kind of a future market in QKD, which is good for us, because it's always good to see that the service providers interested in that, because we are not the ones providing service, we are just delivering the equipment. So there is a commercial market coming up. We're not yet there, but this is kind of like would be the real first step towards something where Europe has its own QKD capabilities in space. This is the vision batch of that. I would say a bit more about that in a few minutes. And yeah, it's a bit dreadful for me. There's also a lot of standardization work coming up these days, and must personally say I'm not the biggest fan of that, but it's also something important. So we are contributing to the national level, DIN, VDE, but also European level in terms of quantum technology and standardization. We have a lab in the company, which was really kind of like fully paid out of company funds. There's no project behind that. So we have 3 optical tables in the clean room. We have well, everything that you need for kind of like a QKD lab. We have superconducting nanowires for single photon detectors for the C-band. We have SPADs in the near infrared range, and we can just play around and test things. So I'm not sure how familiar you are with that, but what's actually the reason why do we want to go to space with something like quantum communications, even though we already have enough problems on Earth? So the answer for that is quite simple. Currently, we don't have quantum repeaters. This was mentioned in the talk earlier. We're working on that, but we don't have that. So the fundamental issue for anything long range related, more than 100 kilometers basically, is losses. So we can't compensate them. It's not like in classical communications where you just crank up your laser, you put in amplifiers or repeaters. That you can't do, of course, with QKD. That's the whole of quantum communication. That's the whole point. So we need to find ways to actually enable long range quantum communication in order to set up networks that bridge oceans, continents, and so on. And this is where kind of like free space communication comes into play. In contrast to fiber-based communication, where you have, due to mostly elastic scattering in the fiber, an exponential loss in the fiber. For free space communication, it's only quadratic in the distance. So that's a much more favorable scaling. Of course, if you do that on ground, you have many other issues. You have line of sight obstruction, trees, mountains. You have the atmosphere. If you travel all the way through the atmosphere. There's no path where there's vacuum, turbulences, and of course, ultimately the curvature of the Earth, which you cannot circumvent. So as far as I know, the longest terrestrial free space QKD experiments were done over 140 kilometers or something like this, and then you reach problems with the curvature. And that's something that is not a problem for space, of course. For if you use free space laser systems from space, you don't have curvature of the Earth problems, you don't have obstruction issues, at least not permanent obstruction issues. Of course, clouds and so on are still an issue. You need to wait until the clouds are away. And the thing that is a little bit of a hidden win for satellite quantum communication is if you're working in a non-stationary orbit, so low Earth orbit, LEO, then actually the satellite moves around the Earth. And that is kind of like, it's like a travel. I mean, if you talk about prepare and measure, that would be kind of a traveling trusted node. Of course, you have to rely on the fact that the thing itself is safe, and one can argue that there's actually problems with that, and we're having this debate heavily with several players. But if you neglect these security issues with something that is in space and might not be in a well-controlled zone, this is a big benefit because you can transfer data between one ground station, the satellite, and in principle just wait until the satellite moves to the other side of the Earth and transmit then the information again. And this is unbeatable in terms of losses, of course. Just to give you a ballpark number, from a low Earth orbit, around 500 kilometers above Earth, in Nadia, that means directly ahead, you have typically 30 to 30 dB losses, which is still a lot. But it's doable with current prepare and measure technology. Just to give you a feeling for what are these kind of losses with laser communication, well, you have, as I mentioned before, obviously diffraction, which is typically the biggest contributor, just like beam expansion, where there's basically nothing you can do about. You have atmospheric attenuation, so this is absorption spectrum of the atmosphere. You have the overall Rayleigh scattering behavior, so lower wavelength has more Rayleigh scattering as longer wavelength, and then you have distinct absorption bands from molecules and so on. So, but you see that the C-band here actually works quite well. There's a lot of misuse, I think, was done in the near infrared around 800, so that also kind of works. So a lot of kind of like gaps where you can work quite conveniently, and basically the average range that you really travel through atmosphere, or the effective range, is quite limited because most of the space that you traverse is empty. The effective thickness of the atmosphere is around 10 to 20 kilometers. Then you have turbulences, which is a different issue. It's not absorptive. It's basically distorting the beam. It's creating speckle patterns. It's moving the beam. This also causes losses. Then you have an intrinsic beam pointing error from the satellite, which just has vibrations and shakes and moves. This also needs to be compensated. And then you have detector efficiency optical losses and so on. But again, this all adds up in a good scenario to 30, 40 dB if you don't have a cloud. Just an overview what has already been done in terms of quantum communication and QPRD from space. Actually, there has been done a lot, mostly from the Chinese and even Asia. So there was MISIUS, which again was kind of a little bit of the Sputnik effect for Europe, which did prepare and measure QKD, entanglement QKD, and quantum teleportation. So the fourth thing. They achieved key rates with prepare and measure on the order of kilobits per second. QKD entanglement rate was pretty small, 0.1 bit per second. Still, I mean, impressive as a first. They did those UK test measurements between ground stations that were, I think, 1,000 kilometers apart. Quite beautiful. But we must admit that we see these numbers and we think that they are a fundamental limitation because with entanglement, you square your losses. So you have the 30 to 40 dBs twice, so 60 to 80 dBs, and at the moment we don't see that you can come up with a commercial product in that range that is meaningful for anyone. I mean, we don't think that 0.1 bits per second, even if you can improve that by a factor of 100, is something that is useful for a customer. That doesn't mean that we're not kind of like looking into this as a future technology, but at the moment we don't think it's realistic. And there were a couple of other experiments, Japanese mission and more recently Chinese missions improving the key rate. The last one is actually quite interesting. This one here on the archive just came out last month or 2 months ago, and the trend is pretty clear. This one doesn't offer improvement in the key rates. It's just much smaller, much more cost efficient than the original Messias mission, and it's quite clear the way they want to go. They want to build up a cluster or constellation, which is now more cost effective. So QKD as a service, as a network. Of course, from a European perspective, that helps us a bit. The European Commission would never use a Chinese secure system. That's good for us. I'm not sure it's good on the global scale, but I mentioned that before. The advantages with prepare and measure QKD from space is that you can use this traveling node concept. The key rates are acceptable. The big issue is the last one. The security implications in terms of having a trusted node in space are a bit unclear at the moment. So that's something that needs to be solved. Whether this is safe or secure and what kind of security measures you need. But this you don't have for the entanglement QKD, but for the entanglement QKD you have other issues, namely low key rates because you have the losses squared. You need to install 2 optical terminals on the spacecraft, which is a hassle by itself because they need to be stable with respect to each other and so on. So there's many. I mean, it just makes the thing more expensive. So in the end, the whole idea or concept behind this is that you have a space segment of a constellation that can bridge long distances, and on ground you have your fiber networks between cities. That's kind of like the network idea that I think is envisioned now by this space industry in terms of that we don't want to replace fiber networks. Obviously, we could never handle the data rates that you need. That can be transmitted over a fiber network. So the challenges in the sub-based QKD market are that it's a high loss transmission. What I haven't mentioned so far is you still need a very strong laser beam parallel to your quantum channel, because otherwise you wouldn't be able to track the ground segment, and you need to constantly realign and kind of like hit the target. For that you need a strong beam, so it's multiplex, classical, strong laser link with quantum channel. You need to filter those because otherwise your classical channel just totally pollutes your quantum channel with a few photons that you have there. That's a big challenge. And in general, what's missing in terms of QKD networks in space is detector technology, especially in the C-band. We don't want to put SNSBDs on the spacecraft for the cryo needs and so on. And there is a high cost associated with potentially security concepts that you need on the satellite. And in terms of certification standardization, something like a unified security proof is still lacking. We have a lot of specific security proofs for specific issues, but if you combine all of those, it becomes very sparse in terms of what has been done, which is a big problem in terms of commercial application, not so much in a research sense. But in commercial application, the customer and the agencies always ask, okay, but that's nice that you have a security proof for photon number splitting, for this, and this, but you need to put them together. So that's kind of things that are still open. Then let me quickly describe this Eagle 1 mission that I was mentioning before. It's kind of, as I said, the first European satellite-based QKD system. It's public-private partnership between the Commission, ESA, and industry. 19 partners from 7 countries. Doesn't make it easier. It's not a lot of coordination work, but it's also quite interesting. It will be full end-to-end architecture. So there's the satellite segment financed through that. There are 2 ground stations financed by that. There's a control center financed. So it will be kind of like a full QKD system. And the planned operation lifetime for now is 3 years, and then there will be the extension possibility if it's interesting by another 2 years. So operational lifetime is 5 years. It will be all wavelength. It will be all C-band, quantum channel, and the classical channel will be C-band. classical and quantum communication will be done optically through laser comms. The most interesting thing is probably, which makes it different from what has been done before, the qubits will not be encoded on polarization, but on phase. And this was a deliberate choice to relax specific requirements on laser communication terminals. So we're using for that mission a standard laser communication terminal out of our portfolio, and those are not optimized to preserve polarization because that is not something that you need for classical communication. So if you use phase encoding, if you prepare two pulses and you change the phase between the two pulses as a means of introducing a qubit, this is much more robust in terms of rotation. It's also something actually that is used in fiber networks much more regularly because in fiber still polarization rotates. So that was the main reason why we did that. I won't go through that. There's some complications or disadvantages related to phase encoding, which are mostly on the receiving side because you need to stabilize interferometers. It's not only passive components where you have polarizers and cubes and so on. You actively need to stabilize interferometers on ground to actually decode the phase information again. And it's also sensitive to frequency drifts, which might not sound like such an issue, but then you have to think that the satellite is moving with the tangent speed of kilometers per second, and the Doppler shifts that you get through that can be several gigahertz. So you need to compensate those dynamically. This is payload of the mission. We're already quite advanced. We're manufacturing the boards right now. The optical head, the modem comes from us, and we're integrating the QKD modules in our company. There are actually two QKD modules for redundancy. So if one fails for now, we have the other one. We're also involved in other R&D projects in our lab. I don't want to go into details of them. We're actually looking into quantum memories. We have a quantum memory prototype study with the DR Institute in Ulm, where we look at developing space-ready rubidium mods. It's just a rubidium mod. It's not for memory. It's just to see whether this is a technology that actually can eventually go into space. We are doing transmitter development, specifically putting transmitters on photonic integrated circuits to make them smaller, more compact, more cost-effective. These are some measurements actually from our lab, where we also measure Cuber and these kind of things. Actually, we're quite happy with Cuber. It's quite good, but I'm not saying it's a commercial product. And we're also looking into future programs in terms of going beyond BD84 protocols, maybe trying something along the lines of continuous variable QBD for inter-satellite link handover. So two satellites that are close to each other, then you don't need a single photon detector in them, which would be an intermediate technology. And then eventually also entanglement sources and also out of QKD, quantum sensing and metrology. And with that, I would like to thank the team. So actually we have, those are all called systems engineers. I'm myself also called a system engineer, but I'm a physicist. The first two guys are also physicists. The first one did his PhD at Cambridge, working on single photon sources and quantum memories. Second one at Stuttgart, Max Planck Institute, working on NV centers. So we are quite a physicist-heavy team. And we also have a PhD student shared right now with the FAU. So we are quite oriented in working together with academia. And with that, I would like to put forward the last slide, which is the advertisement with the Marie Curie doctoral network that we just won together with Christian, which pivots around satellite optical communication. And there is, so it's 19 partners, and there is one topic about QKD networks from space, which will fund the 3 years PhD position located at our site with the academic supervision of Christian. And with that, I would like to thank you for your attention.
Thank you.
I mean, you've mentioned the ground station, right? So if I understand, or if my understanding is correct, so typically we need a very large aperture telescope, let's say on the order of at least meter-ish. Yeah. So and you mentioned also your tiny telescope can be used for ground station? I'm a bit confused.
Yes, not for QKD. We're not using the small one for QKD.
Okay.
This is just general protocol. We're using the other one, the 80 millimeter for QKD, but you're still right. The ground stations for QKD are quite large. So there's one which is already being ready and built in Oberpfaffenhofen with the DLR Institute for Communication and telecommunication, which has an aperture size of 800 millimeters, so 80 centimeters. So it's quite large.
Yeah, okay, yeah. So meaning that we still need a larger aperture, which means a lot of investment, right?
Yes, I mean, the question is always, and this in this regard, that latest Chinese paper is interesting. You can, of course, say that you build something larger on the spacecraft, making the spacecraft more expensive, but then saving on the ground segment. And this is a bit in the spirit of what the last paper from China was. They built a 200 millimeter telescope, I think, on the spacecraft and used much smaller aperture sizes on ground. I think it was 280 millimeters or something like this. So much more portable, much more compact. But this is always a question that is actually not concerning us so much. It's more a network or service provider question. Where do you want to spend the money? Do we want to spend the money on the spacecraft, making it potentially much more expensive? Or do you want to spend the money on the ground stations, which is not as expensive as per unit as a spacecraft, but you need many more. So it's kind of a trade-off.
Yeah, okay. Also, I see that in one of your slides, you briefly, you quickly after go over, you briefly mentioned the connection to grounds link, right? Did you?
Yes.
I think that's one sentence.
Yes,
Quickly go over it.
Yeah, so the idea is really with, especially with Eagle One, due to the fact that it's directly compatible with networks in the sense of phase entanglement, that we don't need polarization compensation and so on, that we kind of like start to do some preliminary tests. I mean, that wouldn't be up to us because it's a ground segment, where, for example, at DLR in DLR Institute in Oberpfaffenhofen, they link it directly to a terrestrial network. So they have the telescope, the ground telescope. They have, and it's all adaptive optics anyway, so that there's a fiber directly attached to the telescope. It's directly fiber coupled. We need that for the SNSPDs anyways. And then they just transmit it further over 5 kilometers, 10 kilometers within the network, for example, from Oberpfaffenhofen to Munich to Harald-Weinfurt or something. So to have this kind of connection to a terrestrial network, that would be the idea.
Thank you again.